Welcome back. This video is on section 6.2, Antiderivatives and the Indefinite Integral. In the last video, we saw that an antiderivative of 2x is big F of x equals x squared. And this is because the derivative of x squared is 2x. Can you think of another function whose derivative is 2x? Well, how about x squared plus 1? If I take the derivative of this, I get 2x. Likewise, if we consider the function x squared plus a million, when I take its derivative, I get 2x. In fact, for any constant c, the derivative of x squared plus c will be 2x because the derivative of that constant is 0. So actually, x squared plus c is the family of antiderivatives of 2x. Once we know one antiderivative, big F of x, for a function, then all other antiderivatives are of this form, big F of x plus c. Let's discuss the notation for the family of antiderivatives of little f of x. We'll use the integral sign. So the integral of f of x is equal to big F of x plus c. And this here is the indefinite integral of f of x, since we're not specifying any limits of integration. So we should talk about the difference between the definite integral and this indefinite integral. With the definite integral, you do specify the limits of integration from a to b in this case, and you always get a number when you evaluate this. Whereas with the indefinite integral, where we're leaving off the limits of integration, you get a family of functions. Just like we had a collection of formulas for derivatives, we can now come up with antiderivative formulas. For example, the antiderivative or indefinite integral of x to the n is x to the n plus 1 over n plus 1 plus c, provided n is not equal to negative 1. And if k is a constant, the integral of k is kx plus c. So let's look at this quick example. Find the indefinite integral x cubed plus 4. Just like with the derivative of a sum, we can break up the integral of a sum and write this as the integral of x cubed plus the integral of 4. And to determine the integral of x cubed, I'll use this power rule up top. We end up with x to the 4 over 4 plus some constant, which I'll denote c1. And for the integral of 4, using this formula here, we end up with 4x plus some constant, which I'll call c2. Now, I could just merge these constants c1 and c2 and call it some new constant c, and that's typically what you'll see. So we end up with x to the 4th over 4 plus 4x plus c. And the nice thing about this is we can always check our work. Whatever you end up with here, you can take the derivative and make sure you get back to what you started with here, what's in the integrand. So if we take the derivative of x to the 4th over 4 plus 4x plus c, we end up with this, which reduces to x cubed plus 4. That checks. That's what we started with, and that's what we have in the integrand. I'll share just a few more antiderivative formulas. An antiderivative of 1 over x is natural log of the absolute value of x plus c. An antiderivative of e to the x is e to the x plus c. And finally, an antiderivative of e raised to some constant k times x is 1 over k e to the kx plus c, provided k is not equal to 0.